Okay, so in this video, we will discuss the concept of linear approximation. Now the idea is very simple. You may use the tangent line to a given function to approximate the original function. So let's look at graphically what this means. And you'll see this is a very intuitive idea, as the tangent line close to the point of tangency is extremely close to the original function. Suppose a function looks something like this. And suppose that we are interested in the values, the y values on this function, around, say, this point. Call it x0. This would be a fixed value of x. Now the function f may be very complicated, so it may be very difficult by hand to estimate the values of the function directly. Well, instead we can use a simpler function, namely the tangent line to the function at this given point. Now if x is x0, the y value will of course be f of x0, the corresponding y value on the graph of our function. And so now we can draw the tangent line to f of x around this point. So this would be the tangent line. And you can see, well, first of all, a line is much simpler than any function you can think of. And you can see, if x is close enough to x0, then the y value on the tangent line is very close to the y value on the original function. And this is the whole idea. For any x value close to the point of tangency, you can see that the y values on the tangent line are very close to the y values on the function. Now it's pretty clear from the picture, and this is the case in most examples, as x moves further away from the point of tangency, the y values on the tangent line are moving further away from the y values on the original function. So you can only use this approximation for values close to the point of tangency. As you move further from x0, the approximation become weaker, and so it's not very useful. Since in any problem that will use linear approximation, we'll need to find the equation of the tangent line to the function at the given point of interest. Well, we'll find a formula for the tangent line to any function around any point, and this will save us a lot of time when we consider examples of linear approximation. Okay, so the equation, of course, is that of a line, so y equals mx plus b. Let's solve for m and b. Well, m is obvious, right? M is the slope of the line at the point x0, but the slope of the tangent line is by definition the derivative of f at the point of tangency. So m is quite simply f prime, the derivative of the function at the point of tangency being x0. Well, let us now solve for b. So at this point the line becomes y equals f prime of x0 times x plus b. But we can use the fact that the line passes through the point x equals x0, y equals f of x0 to solve for b. As the tangent line passes through this point must satisfy this equation. So let's replace. Replacing y by f of x0 equals the derivative of the function at the point of tangency times x, which is now replaced by x0, plus b. So solving for b now is trivial. Subtract on both sides f prime at x0 times x0. And now we can plug back in to the equation of the tangent line our value of b. And so we get the equation that y equals f prime of x0 times x plus b, which we have found to be f of x0 minus f prime at x0 times x0. But we can simplify some more. If you notice, the first and the third term are both multiplied by the derivative at x0, so we'll combine these two terms together and factor out the derivative, and we'll leave the f of x0 alone. So we have f of x0 now plus this term minus this term. If we factor f prime of x0, then we are left with x minus x0, and that's it. And so you see, given any function f of x and any point of tangency x0, this is the equation of the tangent line to the function at the point of tangency. Y is f of x0 plus f prime of x0 times x minus x0. And one last little definition, or I should say notation. Now the line is a function of x, right? A constant plus a constant multiple of x minus x0. And so here's how we'll denote the equation of the tangent line. We'll use a t for tangent. Tangent at x0, so we'll use a subscript x0. Now this means the tangent line at x0, and it is of course a function of x, so t of x equals, let me just recopy this, f of x0 plus f prime of x0 times x minus x0. So there you have it. So finding now the equation of the tangent line to a function will be extremely efficient. Evaluate the function at the point of tangency, evaluate the derivative at the point of tangency, plug it in, and you have the equation of the tangent line to the function at the given point. And as we have just said, the whole idea of linear approximation is the following short statement. If x is very close to x0, let me write this underneath here, as long as x is approximately x0, so if x is close enough to x0, then the conclusion is, well, let's go back. If x is very close to x0, let me exaggerate to really see the difference between the tangent line and the function as they are really close together. Suppose x is here, then you can see f of x is very close to the value on the tangent line. And this is the whole idea of linear approximation. F of x is the y value at x on the original function. The tangent line at x is the y value at the same point on the tangent line. And when x is very close to x0, the y values on the function are very close to the y values on the tangent line. And this is what linear approximation is. And again, from the picture, it's very clear. Take any value x close to x0, look at the y value on the tangent line, look at the y value on the original function, and both of these will be very close to each other as long as x is fairly close to x0. And the idea is we'll want the value on the function, but it will be too hard by hand, and so we'll settle for an approximation being the y value on the tangent line, which by hand will be much simpler. Let us now consider two examples where we will use linear approximation to estimate numbers by hand, and non-trivial numbers at that. So here's the first example. So here's the question. We are going to ask to estimate, or if you prefer approximate, let's go with the root, the square root of 118 by hand. So we're trying to approximate the best we can with what we have so far, the square root of 118. Well, we'll use linear approximation, and if you go back, there are two key ingredients. We need a function and a point of tangency. Well, the function is pretty clear. We take the square root of 118, so the function will obviously be the square root function. Okay, well, we're taking the square root of 118. So we want this y value right here. Now this is not an obvious task by hand. Well, the idea is, let's now use the equation of the tangent line. But there is still something that we have to figure out here, because we have to evaluate f of x0 and f prime at x0. So we need a value of x close to 118, where the square root is a very nice number. Well, you see 118 is close to 121, and the square root of 121 is 11, and this is our x0. So you'll see that because we're doing this by hand, x0 must always satisfy two conditions. The first, it has to be very close to the point that you're interested in. The second condition, it must be easy by hand to evaluate the function at this point. And here both conditions are met, and now we're ready to use linear approximation. So let's just draw the tangent line. To the function at this point. A rather bad line, but suppose this is the tangent line. And now we can find the equation of this line quite easily, right? Let me rewrite the formula we have for any function at any given point x0. It simply is f of x0 plus f prime at x0 times x minus x0. So all we need is f at x0 and f prime at x0, plug it in, and then we're good to go. Well, if f of x is the root of x, f prime of x, thinking of the square root as a power of 1/2, using the power rule, the derivative is 1 over 2 root of x. So let's first find f of x0. This is the square root of x0. x0 is 121, so root of 121, which is 11. Well, what is now f prime at x0? Well, it is 1 over 2 the square root of x0. 1 over 2 times the square root of 121. The root of 121 is 11. 2 times 11 is 22, so 1 over 22. Now we can plug it in and we'll have the equation of our tangent line. So the tangent line around the point x0, being 121, as a function of x ends up being f of x0, 11, plus the derivative at x0, 1 over 22, times x minus x0, x minus 121. And now we have the equation of our tangent line, and we are now ready for our linear approximation. We wanted the exact value of the square root of 118? Well, we don't know how, so the best we can do is take the value on the tangent line at x being 118. And so now using the y value on the tangent line will give us an approximate value to the exact square root of 118. So let's replace in our tangent line the value of x now by the value of interest, 118. And the rest will just be a simple calculation. So we have 11 plus 1 over 22 times 118 minus 121. And let's now simplify this. So 11, 118 minus 121 is negative 3, so negative 3 over 22. Well, we could combine over a single denominator and then give the answer as a rational function, but it'd be nice to give a numerical decimal value to get a feeling for the value of the square root of 118. So here we'll simply use long division. We'll divide 3 by 22. Well, we can fit into 322 0 times. We can fit 22 to 30 one time. We subtract, we get 8. Since we move to the next decimal place, we have to multiply by 10. We can fit 22 into 80 only 3 times, so 66. We subtract, we're left with 14 times 10. Now, if we do 6 times 22, 6 times 20 is 120. 6 times 2 is 12, which gives us 132. And that's the closest we can get to 140 without going over. Sorry, 132. We subtract, and we get 80 again. And you can see now we'll go in circles forever. We'll go back to 80, then 140, then 80, then 140. So we got the 3 when we got the 80, and so we'll get 3, 6 periodic forever. So there you go. The 1 is out. It's going to be 0.136363636 forever, and so now we're good to go. This will be 11 minus 0.136 periodic, which of course simplifies to 10.863 periodic. And now we have our linear approximation. By hand, using the value on the tangent line, we can say that the root of 118 is approximately 10.863 periodic. Which is a non-trivial statement. It's not clear that the root of 118 is roughly this value right here. Again, not an exact value, but an approximation we obtained by hand. If you again expand it, it'd be 10.8636363 forever. And you can ask, well, how good is this? Well, we can ask our calculator. So if you punch into your calculator the square root of 118, you'll find it as approximately 10.8627849, and of course this is an irrational number, so it has an infinite decimal expansion. But you can see that this is pretty good, just by hand. Nowhere in our calculation did we use a calculator, and we obtained this approximation strictly by hand. Now here's what the calculator returns, and you can see that our approximation is pretty good. We are accurate up to the second decimal place, and then we're off here, but point here 27, well 0027 is pretty close to 0.003. So we have a pretty good approximation by hand. And that's it. So this is linear approximation. So always remember two things. Pick your function and then choose a point that will be your point of tangency that satisfies two conditions: being close to the point of interest and where it is easy to evaluate the function at the point, and then you can simply take the value on the tangent line at the given point of interest, and this will yield the desired linear approximation. Let's do one more example with now a cube root. So suppose we say by hand, we wish to again estimate the cube root of 8.07. Now here, I will not sketch a graph of the function, because once you get the idea of linear approximation, the sketch becomes irrelevant. Of course, if it helps you, feel free to use it. Well, as we've said before, we need two things. What is our function? What is our point of interest? Well, we take the cube root of a number, so clearly the function is the cube root of x function. If you prefer, x to the 1/3. Now we need a point very close to 8.07 where the cube root is easily found by hand. Well, this is clearly going to be 8, as the cube root of 8 is 2. To find the equation of the tangent line, we need, if you remember, the function at x0 and the derivative at x0. So let's find the derivative. From the power rule, we get 1/3, x to the negative 2/3. And now let's evaluate both the function and its derivative at x0. So f of x0 is f of 8, which is the cube root of 8, which is 2 because 2 cubed is 8. F prime at x0 is f prime at 8, which is 1/3, 8 to the negative 2/3. Well, here, break this up into two steps. Take the 1/3 power of 8, which is 2, and then 2 to the negative 2 is 1 over 2 squared, which is 4, and so you get that 8 to the negative 2/3 is simply 1/4, times 1/3 gives you 1 over 12, and that's it. So now we can write the equation of our tangent line to the cube root function around the point x0. If you remember, this is the general expression, f of x0 plus f prime at x0 times x minus x0. Let's replace x0, f of x0, and f prime of x0 by the given values. So we have the tangent line at the point 8 as a function of x is equal to f of x0, 2, plus f prime at x0, 1 over 12, times x minus x0, which is 8. So here's the equation of our tangent line, and now we are ready to find our linear approximation by hand. So what do we want? We want to estimate the cube root of 8.07. Well, as f of x is the cube root of x function, this is simply f of 8.07. And now we realize that, well, if we leave it like this, we don't know where to go from here. So of course, we know that because 8 is very close to 8.07, we can replace the function by its linear approximation. So replacing f by t sub 8 at 8.07. Because as long as the point of interest is close to the point of tangency, the tangent line will be approximately the function and vice versa. And now this is quite easy. We can just now plug in, instead of x, 8.07 and perform the calculation. So 2 plus 1 over 12, 8.07 minus 8, 2 plus 1 over 12 times 0.08. And now here, we can be clever about this. Once again, every time we have our linear approximation, we would like to give a final answer in decimal form. So here we'll simply write 0.07 as 7 over 100. The over 100 part is easy, so what we'll do is we'll compute 7 over 12, and then we'll divide by 100, as this is quite simple. So 7 over 12 times 1 over 100, because this will be simply moving the decimal by 2 places. So let's now do long division, dividing 7 by 12. Well, we can fit 12 into 7 0 times. We can fit 12 into 70 5 times. 5 times 12 is 60. We subtract, we get 10. We're moving to the next decimal place, so times 10 is 100. Now 8 times 12 is 96. So we can fit 12 into 108 times. 8 times 12, 96. We subtract, we get 4. Again, we're moving to the next decimal place, which is giving us 40. We can fit 12 into 40 3 times. 3 times 12 is 36. We subtract, we get 4 times 10, 40. And this is where it gets interesting, because now we're going to cycle back to 40. And once we got 40, we got the number 3. And so we'll get back again 3, 3, 3 forever. So 12 over 7 in decimals is 0.583 periodic. So now we can replace in here. This will become 2 plus, but be careful. What we have is 7 over 12 divided by 100, so we have to move the decimal place to the left by 2 additional places. And so we'll get 0.00583 periodic. This is a trivial addition, 2.0058 periodic. And this is it. This is our linear approximation to the cube root of 8.07 obtained by hand. So let's write our conclusion. By hand, we are able to state that the cube root of 8.07 is approximately equal to, in decimal forms, 2.00583 periodic. And this is a highly non-trivial approximation, right? Right from the beginning, I doubt that you could have guessed that this would be the approximation that we would have obtained. Well, once again, you can ask, how good is this? Well, we can now ask our calculator. So if you plug into your calculator the cube root of 8.07, you will find it is approximately equal to 2.005816402. This is also an irrational number, so it also has an infinite decimal expansion. But you can see again, our approximation by hand to the cube root of 8.07 is very close to the exact approximation, right? The first 1, 2, 3, 4 decimal places are accurate, and then we're off at the 5th decimal place by about 2. But this is still really good, again, given the fact that this was obtained by hand. And that's it. This is a linear approximation. There is still one thing that should bug you from our discussion. And what should bug you is the following. How does the calculator do it? How does it give us an even better approximation to any kind of strange expressions like cube roots, fourth roots, trigonometric, logarithmic functions, and so forth. And this is something you'll see in integral calculus when you look at Maclaurin and Taylor series. And the idea is, how did we obtain this approximation? Well, using the tangent line, therefore using the derivative of the function called the first derivative. But if you find the derivative of the derivative, you get what's called the second derivative, and you could then differentiate this to get the third derivative and so forth. And if you use those so-called higher derivatives, this is when you can get even better approximations. But as I've said, this is something you'll see next semester when you take integral calculus. So you'll finally then understand how a calculator actually is able to return these extremely accurate approximations. And that's it.